All right, so I did record a review, chapter exam 2 review, and I did post that to Canvas. So you should be able to watch that. And it's me rambling, so be aware that it's me just sitting at my desk doing the review while I talk out loud. So I reviewed it and it wasn't too horrible. So hopefully you can get something out of it. Um, any questions? We're going to look at chapter 7 today. And since we're unable to do the experiment, I'm going to we're going to watch the video. Hopefully it'll come up. All right, so chapter 7 is on the central limit theorem. And the central limit theorem, as I described last week, simply means that if you have a population whose distribution is not a normal distribution, or even if it is, but if it isn't, if you take samples of sufficient size from that population and you calculate the average of that sample, if you then do a histogram of the averages of the samples, that will be normally distributed. Are you listening? If the underlying distribution is not normal, you need to take samples of size 30 or greater. There are homework problems that ask you that. Okay, I'm taking a sample size of 17. Do I need to know the underlying distribution is normal? Well, yes. If the sample is less than 30, I need to know that the underlying distribution is normal before I can use the central limit theorem. If the underlying distribution is not normal, and I take samples of size 30 or greater, I'm good to go. I can use the central limit theorem. So let's talk about what the central limit theorem is and how we can use it. Okay, so we're going to attempt to watch this video.
Funding for this program is provided by Annenberg Learning.
My computer, but I'm not sure I can hear it through the.
Hi, I'm Pardeep Subedi, and this is Against All Odds, where we make statistics count. Meet the third grade class at Monica Ross School in Ojai, California. 20 rambunctious 9-year-olds who are about to become a living demonstration of how, with the right statistical tools, we can use samples from a population to make inferences about the population as a whole. Remember, we get statistics from sample data, while parameters are generally unknown because they describe an entire population. Here's our population, the 9-year-olds at Monica Ross, lining up according to their height, 50 inches at one end, 57 inches at the other, with most of them clustered around the center, near 53 or 54 inches. This is our population distribution, the distribution of values in our whole population of 9-year-olds in the class. When we plot this out, you won't be surprised by now to see that the shape of the distribution is approximately a normal curve, from which we can calculate the exact mean mu, 53.4 inches, and the standard deviation sigma, 1.8 inches. Okay, now we're going to take some random samples from our population. Here comes the first sample of 4 students. Throughout this example, we're going to stick with 4 as our sample size. Once again, we calculate the mean. In this case, the sample mean, or X bar, which comes out at 53 inches. Now we take a different random sample of 4. This time, the sample mean is 52.25 inches. From a third random sample, we get an X bar of 52.75 inches. From a fourth, a different distribution, but an X bar that happens to be the same as the last. And from a fifth random sample, we get a sample mean of 53.25 inches. We can keep going until we've selected all possible samples of 4 from our population of 20. And now we can plot out all the sample means we calculated. What we get is a distribution of our sample means. Or to put it another way, a sampling distribution of X bar. A distribution of X bar values from all possible samples of size 4. And like any distribution, it can be described by its shape, center, and spread. The shape is our familiar normal curve. The center is the mean of X bar, 53.4 inches, which is exactly what we got for the mean when we calculated it from the population as a whole. But when we directly compare the population distribution to our sampling distribution, we can see that while the center is the same, the spread of the sampling distribution is much less. In fact, sample means are always less variable than individuals. That makes sense. A random sample should include a variety of individuals. From our population, some short, some medium, some tall. The sample mean literally averages out that variety, so we see less variation. There is a precise relationship between the standard deviation of the sample mean and the standard deviation of the individual heights. Here it is. The standard deviation of the sample mean is simply the population standard deviation divided by the square root of the sample size, in our case 4. So the standard deviation of our sample mean is 0.9 inches. Let's see how we can put this fact to use in a situation with more at stake than figuring out the average height of a 3rd grade class. A manufacturing plant for circuit boards. Actually, this is a scene you don't see that much anymore, an electronics manufacturing plant in the United States. Today, many electronic assembly plants are overseas and involve components that are a lot smaller than these. But we are interested in how statistics helps control quality in manufacturing, and those principles haven't changed. A key part of the manufacturing process is when the components on the board are connected together by passing it through a bath of molten solder. If things go wrong, say the temperature of the solder or the speed of the conveyor isn't right, then the connections on the boards will be faulty. Workers can't wait until the boards reach the end of the line to spot a problem that's occurring here. So after they've passed through the soldering bath, an inspector randomly selects boards for a quality check. The score of 100 is the standard, with some a little higher, some a little lower, the natural variation inherent in any manufacturing process. The goal of the quality control process is to spot if this variation starts drifting out of the acceptable range, suggesting a problem with the soldering bath. Here's the distribution of the quality scores, a normal curve centered on 100. Its standard deviation, derived from the company's experience with the process, is 4. So how does what we've learned about sampling distributions help quickly spot when things go awry? The inspector's random sampling of the boards has a sample size of 5. Let's see what happens when we take repeated samples. From our first 5 boards, we get an X bar of 99.4. From our second sample of 5 different boards, we get a different X bar, 101.6. We keep on sampling, calculating each X bar, until we can start building a sampling distribution, which is, as expected, centered on the mean of the population, 100. But it has a smaller standard deviation of around 1.79, as you can see from the formula. Here's how this is useful in the statistical quality process known as the X bar control chart. The inspector plots the values of X bar against time. As expected, there's variation. The goal of the process is to distinguish chance variation from the extra variation that shows something is going wrong. Here's the normal distribution of X bar. If everything is going well, the mean will be at 100. Now recall the 68, 95, 99.7 rule for any normal distribution. Almost all observations, 99.7% in fact, will lie within 3 standard deviations of the mean. Going out 3 standard deviations from the mean gives us what this quality control method calls control limits. As long as the quality scores remain normally distributed with mean 100 and standard deviation 4, That is, as long as the soldering process continues its past pattern, almost all the X-bar points on the chart will fall between the control limits. The process is said to be in control when its pattern of variation is stable over time. A point outside the limit is evidence that the process has become more variable, or that its mean is shifted. In other words, that it's gone out of control. As soon as an inspector sees a point like this, it's a signal to ask, what's gone wrong? So far, we've been talking about population distributions that follow a roughly normal curve. What if we were to take a very different population distribution? The mayor's 24-hour constituent service hotline in Boston answers hundreds of thousands of calls every year. The operators handle everything from simple requests to more complicated questions about city services.
Typically, people call to report things like potholes or streetlights that might be out in their neighborhood.
People put trash out too early, or people have trash out too late, or people aren't keeping their property clean. They call from some street that in a major 4-lane street where they say there's a turkey running down the middle of the street. There was one where a skunk got stuck in a revolving door. I had one recently about a little boy who wanted to request to speak to a park ranger with a horse.
The thing about calls to this and most other call centers is that the length of the calls varies widely.
So the average length of our calls on the 24-hour hotline is about 1.5 minutes, but obviously that can range.
Most calls are relatively brief, but a few can just go on and on. The mayor's hotline answered a total of 21,669 calls in 1 month. If we plot the length of each call, the variable, against the number of calls, we get a distribution sharply skewed to the right. You can see it on this density curve, representing the month's call durations. If we sampled from this population, would our sampling distribution also be skewed to the right? You might expect so, so let's find out, using different sample sizes, starting with samples of size 10. Let's take our first sample of size 10. For this sample, the mean length of the calls is 98.7 seconds. We can start to build a histogram using the sample mean. Let's continue taking samples of size 10, each time finding the mean of the sample and adding it to our histogram. This final histogram is based on 40 different samples of size 10. We can do the same thing with 40 different samples of size 20. And finally, we can do it again with 40 different samples with an N of 60. Now let's compare our sampling distributions with the original population distribution for all calls to the mayor's hotline. The spread of all of the sampling distributions is smaller than the spread of the population distribution. And you can see that the spread of the sampling distributions tightens still further as the N increases. Interestingly, while the smallest sample size with an N of 10 is still right skewed, the asymmetry decreases as the sample size gets bigger. By the time N equals 60, we've lost the skew and the sampling distribution of the sample mean looks pretty much normal. The normal quantile plot of X-bar data from 40 samples of size 60 looks like a pretty straight line, underscoring that our data are normal. This happens because with larger samples, we are less likely to get all big or all small numbers. We usually get a mix. Some X-bars will be above mu, some below. So we get an approximately normal shape for the sampling distribution, even though the parent population isn't normal. What we've uncovered here is one of the most powerful tools statisticians possess, called the central limit theorem. This states that regardless of the shape of the population distribution, the sampling distribution of the sample mean will be approximately normal if the sample size is large enough. It's because of the central limit theorem that statisticians can generalize from sample data to the larger population. We'll be seeing how that can be useful in later modules about confidence intervals and significance tests. Stay tuned. I'm Pardis Sabeti for Against All Odds.
Okay, so the conclusion of this is what I've been saying since last week. One of the nice things about statistics, maybe I shouldn't say it that way, we can look at populations that are not normal using the normal distribution. And that's very, very helpful to be able to do. And that is using the central limit theorem. So for you as students, when you're looking at problems, if you have a population that you know is normally distributed. For example, if you're looking at weights or heights, for example, that class of 20 children, heights are normally distributed. And we could see that when they found the heights of the children and did a histogram, they got a fairly, what we would expect, a bell-shaped curve. But then she started taking sample size 4. Now, you can take a bunch of sample size 4 from a group of 20, and you can see that from the histogram that they created from the different samples. So they took samples of size 4, they found the average of that sample, and then they did a distribution of the sample. And what happened is you still got a bell-shaped curve. The underlying distribution is normal. So this would be the population. And it has some mean, mu, and some standard deviation, sigma. But when they looked at the sample means, so they took samples of size 4 from that population, they got something like this, and it should be approximately the same height. The mean is the same as the underlying population. So when they took these sample sizes of 4 and then found the mean of all those sample sizes, they found the mean was approximately the same as the mean of the population. But the standard deviation, which we call sigma sub x bar, we also call that the standard error of the mean, or the standard error. So we call this the standard error of the mean. We find that it is smaller by a factor of the square root of n. So because you're taking now samples and you're finding the average, and what does the average do? The average takes all the values, adds them up, and divides by the number of values it has. So it takes all the extremes and averages them out. So then when you look at the distribution of sample means or sample averages, the mean is the same as the population, but the standard deviation is smaller. And that's basically all there is to it. The central limit theorem, which we call CLT for short, is one of the most powerful and useful ideas in all of statistics. There are 2 alternative forms. One is using the mean, and the other is when we look at the sum. We don't do any sums in here. We only look at a population where we calculate sample means. We don't actually calculate any sample sums in this course. So there are 2 alternatives, and both alternatives are concerned with drawing finite sample size n from a population with a known mean mu and a known standard deviation sigma. The first alternative, which is what we do in this course, says that if we collect samples of size n with a large enough n, which is 30 or more, we calculate each sample's mean and create a histogram of those means, then the resulting histogram will tend to have an approximate normal bell shape. The alternative is you could calculate the sums of these samples, which we don't actually do. The size of the sample n that is required in order to be large enough depends on the original population from which the samples are drawn. The sample size should be at least 30, or the data should come from a normal distribution. If you know the underlying distribution is normal, you can take sample sizes of any size you want. So for example, the heights of those children, there were 20 kids, and they took sample sizes of 4, but that's okay because the underlying distribution of height is going to be normally distributed. If the original population is far from normal, then more observations are needed for the sample means or sums to be normal. So that example is the call time at that call center in Boston. Decidedly not a normal distribution at all. But when they took samples and increased the number in their sample, the distribution of sample means became more and more normal. So when they took sample sizes of 60, then the distribution of sample means was fairly normal. Sampling is done with replacement. It would be difficult to overstate the importance of the central limit theorem in statistical theory. Knowing that data, even if its distribution is not normal, behaves in a predictable way is a powerful tool. The central limit theorem for sample means says that if you repeatedly draw samples of a given size, such as repeatedly rolling 10 die, and calculate their means, those means tend to follow a normal distribution. As sample size increases, the distribution of means more closely follows the normal distribution. The normal distribution has the same mean as the original distribution and a variance that equals to the original variance divided by the sample size. So standard deviation being the square root of variance, the standard deviation of the sampling distribution is reduced by a factor of the square root of n. The variable n is the number of values that are averaged together, not the number of times you repeat the experiment. Okay, so suppose x is a random variable with a distribution that may be known or unknown. It can be any distribution using a subscript that matches the random variable. Then mu sub x is the mean of that distribution, and sigma sub x is the standard deviation of that distribution. If we draw random samples of size n from that distribution, then we can look at the distribution of sample averages. The distribution of sample averages, which we use a capital X with a bar over the top. So that is the random variable of the sample averages. The distribution of sample averages is normal with a mean that's equal to the population mean, but a standard deviation that is decreased by a factor of the square root of n. So it is sigma sub x, the population standard deviation divided by the square root of n. So here's an example of rolling a die. This is the example that I would have liked to do in class. And I'm not sure that it looks this good, to tell you the truth. The experiments we've done in the past, I'm not quite sure we get so normal a distribution when we roll 2 die. You really have to roll a bunch of them. But if you roll a die, the probability of getting any one face on the roll of a fair die is 1/6. So if you roll 1 die, then the probability of getting any one of the 6 faces is the same. So the distribution of rolling a die is a uniform distribution. The probability of getting a 1, a 2, a 3, a 4, a 5, or a 6 is the same. Now, if you roll 2 die and then you take the average of the faces, so I roll 2 and then I find the average. So I have 2 die, I do. So I got a 7. So the average is 3.5. And if I do that, roll a 2 die repeatedly and look at the distribution of the averages, I get something that's a little closer to a bell shape. And as I increase the number of die that I roll and find the average there, the more I roll the die, so the bigger my sample size, the more die I roll, so the bigger the sample size, I get a more normal distribution. So even though the underlying distribution is decidedly not normal, by rolling multiple die and finding the average of the faces of those die, and then looking at the distribution of the averages, I get a normal distribution. Okay, so using the normal distribution, you're going to use it just like you've done in chapter 6. You're going to use normal CDFs. The only difference is if you're taking samples, you're going to be looking at the distribution of the sample averages. You're going to use sigma divided by the square root of n for the standard deviation. It's the only difference. So you have to decide as students when you're reading the homework problems, does the central limit theorem apply to this problem, or is this a normal distribution? And it isn't exactly difficult. Okay, in a recent study reported October the 29th, 2012, on the Flurry blog, the mean age of tablet users is 34 years. Suppose the standard deviation is 15 years. Take a sample of size n equals 100. Ooh, it's the central limit theorem, because you're now talking about taking a sample from a population, and I don't know if this population is normally distributed or not, but I'm taking a sample that's sufficiently large, I can use the central limit theorem. What are the mean and standard deviation for the sample mean ages of tablet users? So now you're looking at the distribution of the sample averages, which is normal with a mean equal to the mean of the population, and a standard deviation which is reduced by a factor of the square root of n. So what is this going to be equal to? This is going to be a normal distribution with a mean of, what's the mean? 34? And a standard deviation of what? 15 divided by the square root of 100. So this is a normal distribution with a mean of 34 and a standard deviation of 1.5. 15 divided by 10. So this is the distribution of sample averages. Sample means. Now it was really easy for me to calculate sigma divided by the square root of n because the square root of 100 is 10. So I can do that quite easily in my head. Your calculator can calculate this for you. So you don't need to calculate sigma divided by the square root of n and then put that decimal approximation into your calculator. You can just put it into your calculator and your calculator can calculate it for you. We'll show you what we mean. In a recent study reported October the 29th, 2012 on the Flurry blog, the mean age of tablet users is 34 years. Suppose the standard deviation is 15 and we're taking a sample size n is equal to 100. What does the distribution look like? It's normal. So it is a normal distribution. Find the probability the sample mean age is more than 30 years. So normal distribution with a mean of 34, but a standard deviation equal to 15 divided by the square root of 100. And we want the probability that the mean age is more than 30, more than 30. 30 would be over here, correct? So more than 30 is the area to the right of 30 underneath the normal distribution curve. So what is this going to be? Is this going to be a normal CDF? So the lower limit is what, 30, and then we're going to the right. So 30, a really big number. Now, I was doing some Googling on YouTube, looking at some videos for the TI-83 calculator, and I noticed that the instructors on YouTube were using a large number like 1,000, which is okay. I mean, it depends on what your mean is. how big you need to go out, do you use 1,000 or 10,000 or whatever? But they were just using some randomly big number. And you really probably are better off if you watch any of those YouTube videos to go ahead and use an upper limit of 1E99, 1 times 10 to the 99, or a lower limit of -1 times 10 to the 99. Then you're pretty assured that that's a really small number, a really big number. Okay, what's my mean? My mean is 34. And my standard deviation, and I'm going to go ahead and put this in as 15 divided by the square root of 100 so that we can see that our calculator can calculate that for us. Okay, so let's go over to our calculator. All right, so we're going to do a normal distribution. Our lower limit was, what was our lower limit? I don't have it written down. Lower limit was 34. Our upper limit was as far right as we can go, 1E99 with a mean of, what was our mean? Somebody tell me. The mean was 34. So what was our lower limit? Okay, that's good. I can't remember what I had for breakfast this morning, so 34. And then the standard deviation, I do remember. It was 15 when we're looking at the central limit theorem. So we're going to do 15 divided by the square root of 100. So 15 divided by second square root, it's above the square key on your calculator. And we're taking the square root of 100. And I'm going to go ahead and close those parentheses. And again, I know that's 1.5, but what if it were the square root? What if I'm taking sample sizes of 80? So instead of using a decimal approximation, I can put in the exact value. So what's the probability of me getting a value greater than 30 if the mean is 34 and I'm taking samples of size 100 from this population and standard deviation is 15? The probability I get a value greater than 30 is 0.9962. An unknown distribution has a mean of 90 and a standard deviation of 15. Samples of size n equals 25 are drawn randomly from the population. Find the probability that the sample mean is between 85 and 92. Now, this is a little bit tricky because that sample size is a little bit low for me to use the central limit theorem. I would actually have to know that the distribution is normal to be able to use the central limit theorem with a sample size of 25. So this is a little bit iffy as far as a problem goes. Now, the book actually does go ahead and do this. But I'm a little bit concerned about this right here if that sample size is only 25. That's pretty close to 30. So you're probably going to get away with using the central limit theorem. But what's the probability the sample means between 85 and 92? Well, the distribution of sample averages would be normal with a mean equal to the mean of the population, which is 90. And a standard deviation, which is called the standard error of the mean. The standard error would be sigma, which is what, 15 divided by the square root of 25, which is 5. So that's going to be 3. So the probability that we get a sample mean between 85 and 92, we'd use the normal distribution with a lower limit of 85, an upper limit of 92 with a mean of 90. And a standard deviation of what, 3? Same distribution, find the value that is 2 standard deviations above the expected value of 90. Again, if we're looking at sample means, we're using the central limit theorem. Draw a picture, a mean of 90, and we want to know, find the value that's 2 standard deviations above the mean, but we're going to be using sigma sub x bar. So we're using the central limit theorem. Because we're looking at sample averages. So what's 2 standard deviations above the mean? Well, what is that? 2 times sigma over the square root of n is 2 times what? 15 over the square root of 25. Is that 6? So what's 2 standard deviations above the mean? 90 plus 6, is that 96? Again, why are we using for standard deviation? Why are we using 15 over the square root of 25? Because we're looking at the distribution of sample means. We're taking samples size 25 from this population, and we're looking at the distribution of sample means. The length of time in hours it takes an over 40 group of people to play one soccer match is normally distributed with a mean of 2 hours and a standard deviation of a half an hour. A sample size n equals 50 is drawn randomly from the population. So it's the central limit theorem. If I'm drawing a sample from the population and looking at what's happening with the sample averages, then that is the central limit theorem. Find the probability that the sample mean is between 1.8 hours and 2.3 hours. So we have a normal distribution because they tell me it's normal to begin with a mean of, what's the mean? 2 hours? But the standard error of the mean is what? A half an hour divided by the square root of 50? So what's the probability that x is between, what are we between? 1.8 x bar, excuse me, and 2.3? So what's the probability the sample means are between 1.8 and 2.3? So is this a normal? CDF with a mean of 2, oops, a lower limit of 1.8, an upper limit of 2.3, a mean of 2, and a standard deviation of a half divided by the square root. Right. So normal distribution. The lower limit was 1.8. So we're looking for what's the probability if they average 2 hours? If I take samples that the sample average is somewhere between 1.8 and 2.3. So 1.8, 2.3 with a mean of 2. And what was the standard deviation? A half divided by the square root of 50. So 100%, 0.9977. All right, to find percentiles, let's say, you want to find the 90th percentile. When you're talking about percentiles, they're actually giving you the area to the left of that percentile. So if you score on a test in the 90th percentile, that means you scored better than 90% of the people who took that test on that day. So a 90th percentile, 85th percentile, 70th percentile, that is the area under the curve to the left, which is what most of our calculators default to. So to find the percentile, the value that is that percentile, you just find the area to the left, which is whatever the percentile is. So if it's the 90th percentile, it's 0.9. You put in the mean of the population, but if you're talking about finding a percentile for sample averages, you're going to use sigma divided by the square root of n for your standard deviation. So how do you find the 95th percentile for this distribution? Now, at least they increased the sample size on this one. It's 100, so that's good. I think we did that one before and it was 100, wasn't it? So it doesn't matter what the underlying distribution looks like. We can still use the central limit theorem. So the 95th percentile means the area under the curve to the left of whatever this value is, whatever you want to call it, is 95%. So if they give me an area and they want me to find a value, then we're going to use what? An inverse normal? Whoops, gave it away. So K is what? Inverse normal. Area is 0.95, is that correct? 95th percentile with a mean of 34. But we're talking about the 95th percentile for sample means. So since we're talking about the distribution of sample means, we're going to use what? 15 over the square root of 100? Let's go do that real quick. So inverse normal. Area to the left is 0.95. The mean was 34. The standard deviation, we're using the standard error of the mean because we're looking at the distribution of sample means. So that was what? 15 over the square root of 100. And yes, I know that's what. So the 95th percentile is 36.5, 36.5. So 95% of these people are under the age of 36.5. So 95% of these tablet users are under the age of 36.5. 95% are under this age. Or 95% of the sample means are under the age of 36.5. A retail company has a contract for their employees working in product manufacturing and a distribution which says that they receive a bonus pay if they can produce at least 102 products per day that are free of defects. On average, employees produce 100 products a day that are free of defects. The standard deviation is 10. Samples from 50 random employees will be taken and the quality will be examined for 1 day. What's the probability they get a bonus? Slim and none. So what do we do here? So it's a normal distribution with a mean of 100. On a given day, they produce, on average, 100 products that are free of defects, the standard error of the mean is what? The standard deviation is 10 divided by, we're taking a sample of 50. And we want to know if they can do 102 or better on average. What's the probability of getting a bonus? So they have to, on average, produce 102 items or better to get this bonus. So is this a normal? We're finding the area under the curve. So is this a normal? Let's go ahead and write it down. This is the probability that X bar is greater than 102. So on average, they do better than 102 items. So is this a normal? CDF? We're starting at 102, is that correct? And going to the right with a mean of, what's the mean? 100? And the standard deviation is what? 10 over the square root of 50? I adjusted this problem a little bit because the poor people weren't getting a bonus at all. So I lowered the average they had to get. I wanted these poor folks to get a bonus. Okay, let's clear that out. So we used the normal distribution. We're looking at sample averages. We're starting at 102 and we're going to the right. What's the probability that on average they make 102 or more products a day that are free of defects? So 1E99. On average, they make 100 products a day that are free of defects, and the standard deviation is 10 divided by the square root of the sample size, which was 15. So there's an 8% chance they get a bonus. If their criteria is that they have to, on average, produce more than 102 products free of defects, then 8% of the time they'll get a bonus. Okay, so this is some problems from your homework. Because I always get questions every semester. And I've had several in the online class already do this homework, trying to get ahead of things. And I get this question every time. The lengths of pregnancies in a small rural village are normally distributed with a mean of 268 days and a standard deviation of 16 days. In what range would you expect to find the middle 50% of most pregnancies? That's a normal distribution. And it's a normal distribution because I'm not taking a sample. So this is just the normal distribution. Now the second part, if I'm drawing samples, poof. As soon as I start drawing samples, this is the central limit theorem. And what's the difference? The only difference is what you use for sigma. Do you use the standard deviation of the population or do you use the standard error? Okay, so middle 50%. What does that mean? Normal distribution, here's the mean. Mean. Middle 50% would be what? Two values for X so that the area under the curve is 50%. So it's in the middle. So over here would be some X sub 1, let's call it. I'm first looking at the normal distribution. And over here would be some X sub 2. And the area between this X sub 1 and this X sub 2 is 50%. So the middle, 50%. But we have two tails. You have a tail over here to the right, and you have a tail over here to the left. Okay, and to be able to use my calculator to do this, to use an inverse normal, I need to know the area to the left of x sub 1, and I need to know the area to the left of x sub 2. Now, if this area is 50%, what is the area in the two tails? 25 each. And if you can't just figure that out in your head, how do you figure it out? Well, the total area under a normal curve is 1, correct? And if I take off the stuff in the middle, then there's a half in the two tails. But in each tail, there's half of that, correct? So each tail would be 0.5 divided by 2, or 25%. So 0.25 and 0.25. So to find x1, we use an inverse normal. The area to the left of x1 is 0.25. With a mean of, what's the mean? 268. And a standard deviation of 16. To find x2, you do an inverse normal. But now what's the area to the left of x sub 2? Well, 25% is to the right, 75% have to be to the left, or the middle 50% plus the 25% that's over here. So is that 0.75? Now in the second part, you're drawing samples. So what changes? This becomes what x sub 1 bar, the bar over the top of it, and x sub 2 bar. So what is the probability? If I take a sample of 31, what range would I expect to see the middle 50%? So now what do? Same thing, correct? 0.25, 268, but what do you have to do with the standard deviation? Do you have to divide that by square root of 31? Inverse norm, 7.5, 26, 16 over square root of 31. Now, if you have a calculator that can find center, you don't have to do all this. So if you have a calculator that can find the center, you just put the area in 0.5. Let me show you how to do that. I mean, all my examples on the review is defaulting to the areas to the left of whatever value you're trying to find, because that's what most calculators default to, the areas given to the left. But if you have a calculator like mine, now I have one that can do it left, center, right, and then I have another one that doesn't. So what would we do? Oops, that's not what we want. So for example, 0.25, well, actually we're doing center, aren't we? So 0.5 is in the center. What was my mean again? I don't remember. What was the mean? Did anybody write it down? 238? 268, thank you. What was the standard deviation of the population? 60. And then you just go down and pick center. And that will find the two different x's. So the lower limit of that interval is 227.5. The upper limit's 308.5. So it'll give you the lower limit and the upper limit, if you have a calculator that can do center. If not, if it does left, then you simply do what? So 0.25 and it defaults to the left. And that should be the same as the lower limit we got before, which it is. Is it someone in this class that is a TI-83? It might be one of those ladies back there. I had a student online who has a TI-83, and the difference between a TI-83 and a TI-84 is a TI-83, you actually have to type it in. So you have to type in inverse norm, open parentheses, you go to the inverse norm, you pick that, and then you have to type in the 0.25 comma, the 268 comma, the 16, and close the parentheses. Okay, so again, a problem from your homework: salaries for teachers in a particular state have a mean of $46,000 and a standard deviation of $6,800. If we randomly select 20 teachers from that district, can you determine the sampling distribution of the sample mean? Can you? No. Why not? It's less than 30. If I don't know the underlying distribution is normal, that is not a sufficient sample size to use the central limit theorem. So the answer is no, and you're done. You don't have to put anything in for the distribution or the mean or the standard deviation, because if you can't use the central limit theorem, you're done. Now, what about the second part? Can you use the central limit theorem for the second part? If we randomly select 78 teachers, can you use it? Yes. Why can you use it? Because it's greater than 30. So what distribution are you going to use? You're going to use a normal distribution. So that's what they want here. Yes. What can you use? You can use the normal. What's the mean? Well, the mean is the same as the mean of the population, which what? 46,000? And they asked for something called the standard error. And I've been telling you over and over again, the standard error is the standard deviation of the distribution of sample averages. So that is the sigma divided by the square root of n. So whatever that turns out to be, what is that? 6,800 divided by the square root of, what was our sample size? 78, whatever that turns out to be. So this part we're done with. You just say no and you're done. This you say, yes, I can. I can use the normal distribution because the sample size is sufficiently large. And then it says, assuming that you do have a sample size of 78, what is the probability the sampling error is within 1,000? In other words, the sample mean is within 1,000 of the true mean. So now you want to know what's the probability that your plus or minus 1 standard error from the true mean. So what do we need to find? We need to find the area under the curve. Whoop! I love it when it does this to me. There we go. Okay, so if I need to know if the mean is 46,000, what's the probability that if I randomly select a sample mean that it's between plus or minus $1,000? So is this from 45,000 to 47,000? So the lower limit in your normal CDF would be 45,000. The upper limit would be 47,000 with a mean of 46,000. And what's your standard deviation? Is that, what did we get? 6,800 divided by the square root of 78. What's the 90th percentile? Again, they give you the area under the curve is 0.9. So would this be an inverse normal? 0.9 with a mean of what? What was our mean? 46,000. And a standard deviation of 6,800 divided by the square root of 78. And again, how do I know I need to use the standard error here? Because I'm now looking at the distribution of sample means. I'm taking samples of size 78 from the population, and I'm looking at the distribution of sample means. Assuming, now, what's the last part? Assuming that teacher salaries are normally distributed. So now they say, okay, let's make that assumption. Let's say the underlying population distribution is normal. Do I need the central limit theorem? Nope. Because if the underlying distribution is normal, I can just use the normal distribution. Assuming that teacher salaries are normally distributed, what's the 90th percentile? Well, what's the difference? Do I need to use the standard error? Nope. Because I'm now looking at the population, I'm looking at individual scores. So I'm looking at the normal distribution. So I'm not looking at the distribution of sample means, I'm looking at the distribution of the population. So I don't need to use the central limit theorem. Questions? I'm going to let you out for a fall break 12 minutes early. Are there any questions? Yeah, you have to go to class tomorrow, so do I. All right, well, if there aren't any questions, I will see you a week from today. And we will